Hello everyone, and welcome to the Modern Java course. In this video, we'll discuss one of the most exciting innovations in recent years, virtual threads, also known as Project Loom. This is a big change that might actually impact your performance negatively if misused, so stay tuned. Before I proceed, as usual, the code for this and the other videos in this series is available on my GitHub page. So check out this project, start it, and follow me on GitHub. Before we begin, we need to explain why virtual threads are needed. What's wrong with our current threads? The first version of Java was released with green threads. They were implemented by the Java virtual machine, not by the operating system. As a result, they didn't use the full resources of the system and had issues when integrating with native code. But they were easy to control and reliable across platform. They also had low overhead. But the fact that we couldn't use multiple CPU cores that were becoming the standard made them obsolete. Native threads are the default. When we use most executors or just start a new thread object, we create a native OS thread. This thread can grab a CPU core when it's running. It is managed by the underlying operating system and has resources allocated by the operating system. This is a very good thing overall, but it has a cost. Modern operating systems use preemptive multitasking to switch between processes and threads. This makes sure every thread or process gets a fair share of the CPU time to prevent resource exhaustion. OSs are very good at this, but there's an overhead. When switching a thread, the OS needs to save its state and doesn't know what's important, so it needs to save everything and clean up everything. More importantly, the OS doesn't know how many resources a thread will need for its stack, so it needs to allocate a lot in advance. This puts a limit on the amount of threads that an OS can create, or at least limits the viability of many threads. This is doubly true for Java, which has a per-thread heap allocator. This can be very expensive if you have multiple threads. To summarize the discussion, threads are basically a good thing that helps performance. But if we start creating threads for everything we need, we'll quickly hit a brick wall of performance. Java developers found a solution for that. Early on, we created pools to reuse threads instead of creating new ones on the fly. This limits the total number of threads and keeps the code more efficient. For CPU-intensive tasks, this is great. But what about networking? What if 1 million people hit our server in a day? Even if it's a powerful 64-core server with 64 threads, will only handle 64 users at once. Normally, that isn't a big deal. We can knock out 64 requests, then move back and service 64 more, etc. This could have been fine. But that isn't how servers work. Processing a request might require making another request to a different server. A database operation is also a network request to a remote database. During all these operations, we spend our time idling, waiting for the complete request from the user, waiting for a response from the database or a web service. Operating systems have a solution. Socket select. It lets us bind a listener of sort to a socket, then work based on events. When we get the right event, we can use that to read the additional data. Java introduced that with the NIO API, which was introduced way back in Java 1.4. Here's the problem. To use that, we need an asynchronous API to leverage this behavior. This isn't a unique problem to Java. Many languages introduced async await syntax. This made it easy to write event-driven code that would take advantage of selectors. Several APIs provide asynchronous capabilities like that, Webflux, Vertex, etc. But the legacy of Java becomes a hindrance. If one API along the way uses synchronous functionality, it can demolish the performance of the entire stack. Worse, the code is harder to read, harder to debug, and harder to maintain. A stack trace representing a failure would include no context. This is the case in other languages too, and it's very inconvenient. As you recall, networking apps spend a lot of time idling, waiting for network or I/O. Why not take that time and use the native thread for a different purpose? This is how the asynchronous API works. But why do we need them? We can create a fake thread, a virtual thread that will run on top of a native thread, but for all intents and purposes will feel like a native thread. If we make it sleep, it will just give time to another virtual thread. If it blocks or on a network operation, it will just give time to the next virtual thread. In Loom, we would have as many native threads as there are CPU cores. But this is seamless to us. We don't see the native threads in the code. A virtual thread is assigned to a physical native thread where it runs as usual. This native thread is called a carrier thread. Other virtual threads wait like in any multi-threaded application. The big difference is that the scheduler is a part of the JVM and not a part of the operating system. This is a crucial difference. Since this virtual thread is in Java, the VM knows the exact amount of resources necessary and can add resources dynamically if needed. So the cost is minimal. A regular thread can take up 2 megabytes of overhead in memory alone. A virtual thread starts at 1 kbyte of RAM. We can create 1 million of them without breaking a sweat. If this thread is now blocking, then the virtual thread implementation will just move it off the native thread and replace it with a new thread. This is pretty seamless to us for the most part. But there are some catches. Imagine if we had a pool of virtual threads. Then we'd have a fixed amount of virtual threads on top of the native threads. This would defeat the purpose of virtual threads. When we need a virtual thread, we must always create a new one. Another caveat is pinning. A virtual thread can grab hold of the current thread and prevent its release. This thread will keep working, but the scheduler won't assign another virtual thread to its carrier. That might be reasonable if it happens every now and again for a short period, but might be expensive. Imagine the threads on the left would suddenly get pinned, as if you lost 2 CPU cores and need to keep going with only 2 CPUs left. The main problem in pinning is native code. This makes sense. If we have native code in the stack, the native code might depend on the thread. Unfortunately, at this time, synchronized keyword also triggers pinning, so you should try and minimize its use. Hopefully, this will be fixed by the general availability of Loom. Reentrant Lock and other locking mechanisms aren't impacted by this problem and have many advantages over synchronized, so you should probably use them. When running with this flag, we get stack traces in the console to cases where a pin thread blocks while it's pinned. If the output is too verbose, you can replace it with the short version. But how do you use it in the real world? While we can show Loom on a regular Hello World project, I think most of us would use it in a Spring project. To get started, we need to open the Spring Initializr project at start.spring.io. I picked Maven and Java. I picked the current version of Spring and entered my package name. I added Spring Web, MySQL driver, Spring Data JPA, the DevTools, and Lombok. Those aren't necessary, but we will use them to show off some Loom oddities. Notice you can see the full project in the GitHub link in the video description. Loom is a preview feature in Java 19. To use Loom, we need to make some changes to the project. First, right-click the project and select Open Module Settings. In the settings, make sure to enable the language level that includes the experimental features. Unfortunately, there are several additional changes we still need to make to get this working. In the Run menu, we need to edit the Run configuration option. In that option, we need to add the --enable -preview option. So when we run the project, the preview will be enabled. Notice that the VM option might be hidden in IntelliJ. If you can enable it by selecting Modify Options and checking the Add VM option flag to show this. Once you do that, it should appear where you expect it. Finally, we need to edit the pom.xml file and add a Maven compiler plugin entry so we can define compiler arguments. Here we need to add the --enable -preview option again. Without this, the Maven build will fail with an error. Once we do all of these, the project will run and let us work with the Loom code. To run this, we need a local instance of MySQL. This is something you can run locally or simply use this Docker command to do it. Once you do that, you will need to log into the MySQL server and create a database. I used this command to log into the Docker command prompt, and once I was there, I used the MySQL command line. The password is root. Then I just created the database named DB and exited. We can now connect to the database. In the Spring project, we need to configure the URL and all the settings as such. Notice that the new version of Spring Boot expects MySQL 8 dialect class. To enable Loom, we need to add these two beans to Spring. We can do this in a configuration or just here in the main application, as I did in this case. The executive framework is usually used for thread pools. In this case, the virtual thread per task executor generates virtual threads instead of regular threads or pooled threads. The first one is used for all the asynchronous calls, and the second is used for every request that arrives through Tomcat. That means all web calls will get a virtual thread assigned. I'll skip the database code and go right to the REST request code. This is a trivial API. One writes a database entry with every request and the other doesn't. We'll focus on the one that doesn't, since the API has fewer side effects. I will use the AB tool from Apache to benchmark. This is highly flawed since I'm running on my local machine, but it would give us a bit of a sense of the potential behind Loom. This is the output of running without Loom. This is the output with Loom. Let's look at them side by side. Notice the bottom set of values. They represent the number of requests that took a given amount of time in milliseconds. You'll notice that 50% of the requests for both Loom and regular threads have a similar 20 millisecond run. Loom doesn't improve performance, it improves throughput. As load becomes heavier, the regular thread starts showing overhead, which we can see in the longest request on the left, which is 129 milliseconds, whereas the Loom version is only 42 milliseconds. There are many pitfalls when working with Loom. Some things don't perform faster and might in fact perform slower. But the power of Loom has great potential. We need to benchmark and use the tools at our disposal, make sure it performs well. In the next video, we will discuss pattern matching in switch statements. Follow through the videos to check out the full course. If you have any questions, please use the comment section. Thank you.